Physics Dambusters by Dharmik Shah. The Dambusters project took place between the time intervals of spring 1942 and the mid of May 1943. This was the time of World War II, and the movie revolves around the mission to attack and successfully breach the German dams of Mörner, Soper, and Eder. Now let's talk about the importance of this mission. The importance of this mission was that it would give the Allies a huge advantage in the war effort. These dams, when full, would hold 400 million tons of water. These dams also provided hydroelectric power for the Ruhr Valley, which contained many war factories that funded Germany. Destroying these dams would destroy many of these war factories in the valley. It would temporarily halt the German war effort. So the objective was to destroy the wall of these dams. The Allies knew that they had to bomb the dams, but they didn't know how to do it. They couldn't simply float a bomb across the water, as there were booms that would stop it from advancing. They also couldn't torpedo the dam from underwater, as these booms supported underwater torpedo nets to stop incoming attacks. So what exactly could they do about this? Barnes-Wallis, the lead scientist in this operation, suggested dropping a 10-ton bomb from 40,000 feet in the air that would impact the bottom wall of the dam, eventually exploding. He reasoned that the shockwaves caused by this explosion would erupt the dam, and this is much like an earthquake which releases shockwaves to the ground. However, there were a few problems with this proposal. Firstly, at that time, no airplane could carry a 10-ton bomb from 8 miles up in the air and drop it with complete accuracy. Even if the bomb was off by 50 feet from the wall of the dam, the cushion of water between the bomb and the dam would absorb mostly all of the shockwaves, barely scratching the dam. This photo to the right shows what the bomb would have done from 40,000 feet in the air. Even if it was off by only 50 feet, it would have done almost nothing. The cushion of water was just that strong. And so his second proposal was to have a plane carry the bomb and drop it. Instead of just relying on luck of dropping it and hoping the ball strikes, this time the ball would bounce across the water and definitely collide. His proposal was to have the bomb impact the dam by means of bouncing, roll to the bottom of the dam, and at a depth of 30 feet while still touching the dam, explode. The cushion of water this time would act in their favor, and the shockwaves would go right through the dam, completely demolishing the dam, as shown in the picture where they tested this idea. After Wallace did his math, the general idea became to have a plane fly at 60 feet above the water at nighttime with a ground speed of 240 miles per hour and drop the bomb 600 yards from the Mörner Dam. Then the bomb would bounce across the water, skipping over these booms, and eventually strike the dam. Then it would sink 30 feet below the dam, and then explode, destroying the dam. If the speed wasn't correct, the bomb would either not reach the dam or simply go over the dam, which would be useless. The people involved in this operation was first and foremost Barnes-Wallis, the lead scientist and inventor of the so-called bouncing bomb. Secondly was Sir Arthur Harris, the head of the Royal Air Force Bomber Command, who gave permission for Wallace to continue with this operation and provided him with the appropriate facilities that he required. And finally, there was Guy Gibson and his squadron number 617, the aircrew that were responsible for deploying the bomb at the dams. The testing of this type of bouncing bomb began in Wallace's own home, using an apparatus as such. He used marbles that got their initial momentum from a spring, and then he fired it at a bucket to see if it would bounce or not. When he was confident with this idea, he moved to a bigger testing tank, like the one shown on the right. Using the data he got from the testing tank, he could conclude that the bomb would definitely bounce across the water and eventually strike the Mörner Dam wall, as shown in this picture over here. But seeing everything before it happened was easy enough. The real challenge came with the pilots, as there were targeting difficulties when flying the plane. The two problems were correctly positioning the plane's vertical displacement from the water at 60 feet, and also releasing the bomb at exactly 600 yards. Back in World War II, the plane did not have extremely sensitive altimeters, devices which measured their vertical displacement from the ground. They needed to be exactly 60 feet or 18 meters above the water. This could not be done by the altimeter. Also, how would they know exactly when they are at 600 yards or 500 meters from the dam? Even guessing would be fatal, resulting in the bomb not reaching or going over the dam. These were the difficulties in targeting, and both their solutions resulted from trigonometry. To solve the height problem, Gibson placed two spotlights, one under the aircraft nose and the other under its body. and tilted them to an angle theta from the vertical so that they would align at 18 meters. Since they knew the distance from the nose to the body was 6 meters and the height was 18 meters or 60 feet above the water, they could divide this triangle into two right-angle triangles. From there, they could use simple trigonometric properties to calculate angle theta from the vertical. That's how much they needed to tilt these spotlights. At exactly 18 meters above the water, the lights would converge. As you can see from these images, when the lights are getting farther away, that means you are too high and going higher. Slowly, as you come down to 18 meters, the lights will come towards each other and eventually converge, indicating that you are at the correct height. Similarly, the same approach was used in the second targeting issue. The pilots used a newly created handheld device that they looked through to perfectly know when to drop the bomb. When the pilots were flying in the middle of the dam, the two towers at the edge of the Murner Dam would be exactly 90 meters away from the aircraft on both sides. They knew that they had to drop the bomb from 600 yards or 550 meters away. This again sets up a triangle, as shown in the picture to the right. From this, calculating the angle at which the device's arms needed to be apart was simple trigonometry. As shown in these photos, when the plane was farther than 550 meters, the towers would be in their focal view. As they slowly approach 550 meters, the angle would become just right, and the towers are exactly at the edge of their views. This is when they need to drop the bomb. Let's talk about the bomb itself. The bomb was dropped in a way that it would bounce or skip over the water when it landed. The bomb originally had some velocity in the forward direction that was equal to the plane's ground speed. Also, the bomb was given lots and lots of backspin, which played a key role in the bounce. When the bomb was released, it was in freefall, and so the net force acting on it was gravity. Now, why exactly was the bomb given backward spin? The reason is because this backspin curves the ball upwards in the air, and so that when it hits the water, it will hit at an almost parallel angle to the water. Think about when you skip rocks across the water. You don't throw the rocks in an upward parabolic motion like you throw a basketball. Rather, you throw it downwards in an almost parallel flick like the picture shows here. The flatter you skip the rocks across the water, the more likely the rock will skip. The same principle applies with the bomb. Now let's see the difference this made. Firstly, when this ball is dropped flat, it drifts in the air a lot, and in the water it would simply sink. But let's look at this other one. When the ball is given some backward spin, it curves in the air. It actually seems like it's going upwards, and it travels a much straighter projection, and it aligns itself with the water. It even bounces once. Why does giving backspin do this? This happens because of something called the Magnus effect, which affects all rotating balls and cylinders that fly through the air. Basically, the idea is that oncoming air traveling towards the bomb has two paths that it can take. It can either go above or below the bomb. Above the bomb, the air will travel in the same direction as the spin. The air would therefore follow the spin and get accelerated downwards by the bomb. On the bottom of the bomb, however, the spin is towards the forward direction while the oncoming air is backwards. This airstream slows the bomb down from the bottom, and the air simply travels through. And so the net result is that the bomb causes the air to go downwards. In other words, the bomb exerts a downward force on the air. Therefore, following Newton's third law, the air must exert a force on the bomb upwards, and this is the Magnus force from the air. The Magnus force strength depends on the spin of the bomb. Gravity is stronger, and therefore the bomb will still go down, but since the Magnus force pulls it up, it allows the bomb to level itself, and the impact with the water is at a minimal angle. So that's why spin is important, it levels the ball. Now let's talk about the physics of why the bomb actually bounces. When the bomb is almost level with the water, it travels with the water rather than diving into it and sinking. When the bomb hits the water, there are two additional forces acting on it other than gravity. The first force is the force of water drag acting on the bomb, slowing it down. The second force is the water's reaction force. When the bomb hits the water, it exerts a force on the water perpendicular to it, so downwards. Therefore, following Newton's third law, the water must exert a force equal and opposite in direction to the bomb, which is upwards. Since the bomb is in the water for very little time, the force of the water acting on the bomb is much greater than the force of gravity acting on the bomb. As a result, the bomb comes back out. Since the bomb originally had velocity in the forward direction, and now in the upward direction, when it comes out, these two velocity vectors add up, and so we see the bomb following a parabolic path above the water. The Magnus force is still present when it comes out of the water because it's still spinning, and so it allows another bounce to occur. Finally, we can talk about the momentum. Since the ball has lower vertical displacement and horizontal displacement after each bounce, the kinetic energy is not conserved. The bomb loses kinetic energy because of friction, air resistance, and because of the water. Thus, the collision with the water is inelastic. The momentum of the bomb can be calculated using the formula momentum is equal to mass times velocity and entering an appropriate direction. The kinetic energy of the bomb is transferred to the water every time it collides, and so we would see a decrease in the momentum of the bomb and an increase in momentum of the water. Thus, the momentum is still conserved. When the bomb eventually collides with the water, the momentum in the forward direction is virtually zero. Since the bomb still has momentum because of gravity, the bomb sinks. Due to the backspin, the bomb rolls along the wall of the dam. Eventually, at 30 feet below, it explodes. The water absorbs some of these shockwaves, but since the bomb is touching the wall of the dam, most of the shockwaves are transferred right through, and it blows it up. This attack was very successful because it resulted in the breach of both the Murner Dam and the Eder Dam. It resulted in catastrophic flooding of the Ruhr Valley, and over 1,600 people died on the other side. However, 8 Lancasters did not make it back from this attack. This attack was famously known as the Dambusters.